this astable multivibrator that we are going to discuss now, it actually can be designed using different circuits. You can use an op-amp, you can use a transistor, you can use a 555 timer, okay. It's something like the function is the same, okay, but the circuit will be different. But then since this particular unit is only based on op-amp, okay, we are just going to design it using an op-amp and trying to understand the basics of it. We are not going to go into too much detail, keeping in mind the syllabus, okay, in the time that we have in our hand. So I'm just going to talk about this topic only for this particular class, okay. But believe me, it's a long topic, okay. But some of the things I think I'll just leave it to you so that you can actually understand it, okay. But I will just give you a brief, okay. Enough for exam, for understanding purpose, probably you have to just do a bit of self-study. For example, Schmitt Trigger. Schmitt Trigger is something which is there in most of the undergraduate courses, okay. That is actually used in astable multivibrator. So where can we use it? Okay, as I said, it can be used to design a relaxation oscillator, okay, oscillator. And when we talk about a relaxation oscillator, it simply means that output, okay, is non-sinusoidal. When I have introduced this topic, okay, we actually talked about different amplifiers. I did say that relaxation oscillator is nothing but having an output which is non-sinusoidal. So if you have an output in a CRO, we use a cathode ray oscilloscope in our lab typically, okay. We can actually see that CRO can have a triangular wave or a square wave as an output, and that is actually nothing but a relaxation oscillator circuit which works. If we have a sine wave, probably any other circuit is working within that CRO. Okay, so there are different circuits, and it can be switched from one circuit to the other circuit. Okay. So the first thing is a Schmitt trigger. A Schmitt trigger is something based on which are actually oscillate multivibrator, astable multivibrator usually works, okay, and a Schmitt trigger usually uses an op-amp, okay. So I will just draw the circuit for a Schmitt trigger, okay, and whatever is important probably I'll just tell you guys those points, okay, and some of the things might be you have already studied, okay. So we have it here, then there is a resistor here. So for me, when I was doing my master's, the most difficult part as far as electronics is concerned is probably not the understanding part, but remembering so many circuits. And this is something which is going to happen with all of you, okay? So I suggest all of you to please draw all the circuits and probably please sit in front of your study desk so that you can actually kind of look at them every day, and probably it will be something which will be very natural to you. Okay, so this is there, okay, and you basically have input, okay, a part of it is actually given, okay, the input, a part of it is given. Why part of it? Because if I have the output, I'm not providing the entire output to the input, okay, as a feedback. Let's say this is R1 and this is R2. Whatever voltage is there across R1, that is actually being provided as an input, okay, for the circuit to work. Okay, and depending on the input, suppose I have got an output, some volt, okay, and that voltage would be, let's say, the saturation voltage. In general, we say that that's the maximum voltage, okay. So in general, if I write it down here, okay, we will include it in our main notes later. This V output may be the saturation voltage, that means the maximum voltage, okay, and out of that some voltage is getting extracted and actually fed into the non-inverting terminal. So depending on what is the voltage here, is this voltage greater than V in or less than V in, okay, we are going to get the high or the low signal, okay. That is actually how a Schmitt trigger usually works, okay. So this is actually a circuit diagram of a Schmitt trigger. So if you have followed this book on DC Tayal, okay, it has got a very detailed analysis of Schmitt trigger, okay. You can check that book. Schmitt trigger. Okay, so that's Schmitt trigger. Okay, and here basically, if we are basically considering Schmitt trigger, it is basically having two threshold voltage. Threshold voltage. So we all know what is threshold voltage. Okay, that's the limit. Okay, it doesn't go beyond that. And then this threshold voltage, okay, the one is the upper threshold voltage, okay, upper threshold voltage, and here we are basically going to have triggering, okay, Schmitt trigger basically, so triggering from low to high. So this is low to high, okay, and let me just say this is upper triggering, so we just write it down as VT, okay, and then you can actually have lower triggering, okay, and then that will actually be something which will take place the other way, that is high to low, okay, then I'll just denote it as L. So this is actually a Schmitt trigger, okay. The theory is quite big. I'm not going to ask you a question on Schmitt trigger. I'm just telling you this because we need to understand it, okay. So this, whatever value you have, let's say you're basically having a value of beta, okay, and then you have got taken some part of the output, let's say beta V naught, okay. Now if this beta V naught, okay, that's the feedback gain factor. Basically, if this beta V naught is less than V in, okay, you are going to have a circuit which behaves in a different way. And if this beta V naught is greater than V in, it will be acting in a different way altogether, okay. So this triggering will happen depending on what is the value of this beta V naught. And that is a very superficial idea of working of a Schmitt trigger, okay. But then we are discussing here an astable multivibrator, so we'll probably just draw the circuit diagram for our astable multivibrator and then try to go for the understanding of that, okay, based on that circuit. So let me just draw this, okay. So what I'm going to draw is a Schmitt trigger, okay, and then we are going to just have some changes or additional parts here, okay. So we'll have this. So let me just redraw this, okay. So then I'm going to copy that, okay. It's not going to take much time. Okay, so that's that. And what happens is that we are actually having a non-inverting terminal, okay, and as op-amps really work, we are going to have a feedback resistor, okay. Please don't make mistake while drawing the op-amp circuits, okay. All the circuit looks almost the same. There are certain differences, okay. It's like it might have an additional component, okay. So in this particular case, in general we have a resistor here, but we don't have a resistor in this particular case. In astable microvibrator, we are actually having a capacitor, okay, and this is the circuit for this. And I'm sure all of you are going to make a lot of mistakes while drawing the circuit diagram if you don't practice. So I'm giving you this warning beforehand, okay. This is the non-inverting terminal. And then we have this. Okay. Let's try to level this out. Okay, let's mark this point as E. Okay, this is your capacitor. Okay, and this is your feedback resistor, but I'll just write it down as R. Okay, and then this is R1. This is R2. Okay, and then this is basically nothing but V out. Okay, and this is the circuit of an astable multivibrator. Astable multivibrator. So when I ask you for the circuit, you can draw this, okay? And Schmitt trigger, you should know, I've just drawn this separately. So if you don't consider this E, don't consider this R, it is basically nothing but a Schmitt trigger, okay? And you know, this is actually based on how triggering happens, and that's why we are actually going to use a trigger, okay? So in general, what happens is that this V out, okay, if we are not considering any kind of input in the initial stages, is equal to nothing but V. Let me write down the entire word here, saturation. Saturation, okay, initial. This is the initial condition, okay. And before I write down the sentences, let me just tell you this very simple idea. What happens is you basically are going to have some part of the voltage or V out, okay, not some part. In fact, the V out getting fed back, okay, in terms of the gain factor, okay, into this particular line of circuit, okay. And here you know there is a capacitor, So as soon as the capacitor starts charging, there will be a development of voltage, and some voltage will, this voltage will actually appear across A. Okay, as a result of which we can say that we are actually having an input in this side. Okay, we are actually having an input here. So that means we are already having a voltage here, okay, based on this particular circuit. At the same time, we are also taking a part of the voltage at this particular part, which is actually nothing but based on beta, right? So we have a voltage at this in non-inverting terminal, and we have a voltage at the inverting terminal, okay? And if you remember, let's say the comparator circuit or a circuit where actually having an input on both the ends, okay? Based on this, we can actually have the triggering happening, a high or a low system happening. But then what will be the voltage here, okay, will depend on whether the capacitor is charging or discharging, okay? So the charging discharging cycle will actually decide what is the voltage at this particular point, and this charging and discharging will depend on whether the voltage here is higher than this or lower than this, okay? So this is the first idea that you should remember, okay? But let's just write down the or draw the circuit, okay, part by part. Maybe you can just okay. So I'm just going to draw the circuit part by part and then going to explain one part after the other, and that I think should be okay. Okay. So let's say I have one line here, okay, and I have one line here. Both are equidistant from the center line, okay, and okay, I will probably just try to make it a bit different here, okay. I'll just try to make it as dotted lines, so that will be different. Or rather, just give me a minute. I'll change the color of my pen. I think that is far more convenient. So this is going to fluctuate between high and low, okay. And when we say saturation, let's say this is the saturation value, okay. Let's draw the graph now. Let's say this is your saturation value. So I will mark this as V set, okay. So you can have a saturation value on the positive as well as the negative one, okay. And let's just okay, and so what happens is that the capacitor will usually start charging, okay. So let me write down the first point, okay. The capacitor, okay, starts charging. Try to understand this, okay. Let's take it slow. The capacitor starts charging via V out path. So if you look into the diagram, you know that the capacitor will actually start charging this via V out path, okay. So V out path, okay. So and then if we just want to show charging, okay, how do we exactly show charging here, okay. Do I have another option? I can take this color, okay. So this will basically be something like this. The capacitor will start charging. As soon as it reaches certain voltage, you are going to get a high signal, and that high signal will be fixed. It's at V saturation value, okay. So this is the first step that we are actually talking about, okay. And then what happens is, if we are basically considering, let's say it's an ideal op-amp, okay. Let's say we have got an ideal op-amp, okay. I cannot go to the next page, otherwise it will be very difficult to follow, okay. So just go this ideal op-amp, okay. So if it's an ideal op-amp, so basically we know that there will be no current, okay, is flowing, because the input impedance would be very high, okay, into the op-amp. Once the feedback starts, there will be no current which will flow into the op-amp terminal, okay. And then let me just mark this as A, okay. Mark this as A. and then what is this A? As C charges, okay, this charging will happen, okay, voltage, okay, builds at A. This is what I said, okay, you can just repeat the diagram. The voltage will start building at A, okay, okay. Also it will happen at A also, as well as at the charging point, okay, and will reach the upper threshold voltage, upper threshold voltage, okay. So it will reach the upper threshold voltage. So that means if I say A, that means I'm talking about this particular point. This is A, okay, this is this A. So got one part of it, okay. Let's write down what is B. B, what happens is, as voltage, okay, at, now this is what is the property of a Schmitt trigger is, okay, as the voltage at the inverting, that means the minus terminal, that means the point at which A is connected, okay, inverting node A, okay, is slightly more than the non-inverting node. So what happens is that if this particular voltage, the voltage at node A is slightly more, if this particular voltage at this particular point A, okay, is slightly greater than this particular point, okay, the capacitor is going to start discharging, okay, and that is how a Schmitt trigger usually works, okay. So you know what happens usually if you consider something like a Schmitt trigger is that if you are considering any kind of electrical signal, okay, it's not that you are going to have a ideal case where this will be something like this at high and something like this at low. No, that doesn't happen, okay. In general, an ideal case would be it will fluctuate, okay, but it will be actually fluctuating at certain range, okay, and then probably it will just go down and fluctuate at this range, okay. But when we are actually using such circuits at the fluctuating value where it is nothing but within certain range, let's say it is between fluctuating between 5 to 5.5 volt, okay, it is going to give you a constant supply of, let's say, 5.2 volt. On the other hand, if it fluctuates between, let's say, 0 to 0.5 volt, it might be giving you a constant value of, let's say, 0 voltage, okay. So this is how our Schmitt trigger usually works, okay. You're going to get a certain value. So what happens is this is fluctuating, the capacitor. So it's at certain value, you're going to get that high value, okay. But in the next range, what happens is this actually will start discharging. So as soon as it starts discharging, okay, let's say it reaches at this particular point, okay, what we are going to have is the signal will actually go down, okay. So we are going to have a signal which actually will go down, okay. This diagram is not very perfect, this should come here, okay. This from here, yeah. This is okay. Will come here, okay, and then we will actually have the negative saturation value. So it's not that the negative saturation value is going to be exactly at the point where the capacitor starts discharging, okay. So this is minus V set. So let's say it's up to this particular point, okay. It will be equal, okay. So this particular range is basically nothing but what we are talking about in terms of B. So this is B. This is B, okay, discharging. And when does this happen? The voltage at the inverting node A, you have to remember this, the voltage at the inverting node A is slightly more than the non-inverting node. Now why this discharges when this is more than this is something which is explained in a Schmitt trigger, okay. So I would suggest all of you to please look into Schmitt trigger, and probably I'll try to explain this in the next class, okay. But right now let's just try to complete this topic, okay. So this is a condition that you have to remember for exam purpose, but for understanding purpose you have to go back to Schmitt trigger and try to understand this. But you know, Schmitt trigger is a very large topic, okay. So now what happens is, again, it might happen that because of this feedback fraction, the voltage will actually keep fluctuating. The capacitor will start charging again, okay. So now as voltage, okay, goes below minus let's say beta V set, okay, minus beta V set saturation. Why minus? Because you know it's actually applied into the inverting terminal, okay. V set beta voltage, the voltage voltage at the positive terminal, okay, terminal will be, now the voltage with the positive terminal will be slightly more, okay, than negative terminal. Now the other way it happens, okay. Now at this particular point, the voltage will be more, and this particular point the voltage will be less. As soon as this happens, okay, the capacitor will actually start charging, okay. And when this capacitor starts charging, okay, so this is actually minus beta V set, okay, this, okay. So as soon as this happens, this capacitor will start charging and we will get something like this, okay. As soon as we get this, what we are going to get is high end, okay, high voltage. So now we are going to get this. Difficult to do it stage by stage, but I'm just trying to do it with it. Okay, and then we have it again at this particular point. And this is something which is going to continue, okay, and we are going to get the different part of the circuit, okay. So this is C, this is C. This is what happens at this particular point, okay. So I'm trying to keep it simple so that all of you can understand this. That's why I've marked it here ABC, and here also ABC, and this is how you can explain it, okay, in your exam also. So this is minus V saturation. You can have a positive part and the negative part. This is again V saturation, and so on. So it's going to fluctuate between these two values, and it's going to be high and low. High when the capacitor is charging, low when the capacitor is discharging. When does the capacitor starts charging? Okay, when this condition happens, okay, B V set minus beta V set at the positive terminal, basically the voltage is more compared to this, the capacitor will charge. If this voltage is more great compared to this, the capacitor will start discharging, okay, and based on this we can actually have a high and a low signal. So for your exam purpose, I think this is important to understand, okay. And in this way, if we just continue, what we are going to have is the different charging and the discharging states, okay. So then again the thing repeats, okay, and then it happens. So you know, if this is A, that means the beginning, and then it is B, then it is C, then this will be again B, okay, this will be again B. This is the initial state, okay, and this will be again B. So maybe I can just write down this as B. Okay. So this will keep happening, okay, and I know it's not easy to understand it at one go. I just suggest all of you to please sleep over it, try to understand it, okay, take some time. So we'll again have this, then we'll again have this, and this cycle of charging and discharging will keep on happening, and there will be this square wave that is getting generated. In fact, if you're actually using a CRO in your lab, okay, this is something which actually happens inside that, okay. This is the circuit, and this is how it works. So you know, op-amp is actually a multifaceted electronic component, okay. It has got a lot of property, and everything can be more or less explored for different purposes, okay. What I'm going to not derive is something this, but there might be a numerical question, so that's again important, okay. What do I exactly mean by time period? So maybe I will just mark this, and then we'll go back here, okay. So if I just tell you what is the time period here, time period is this, okay. If you go from here to this particular point, okay, this is nothing but your time period, okay. This is your time period. So let's just write down a formula for time period. That's it, okay. Just going to write down the formula for time period because we are trying to derive this, so we're not going to derive it, okay. Font a bit larger. Okay. The time period T actually will depend. So how much would be the time period, okay? At what point you are going to get a high value, at what point you are going to get a 0, okay, at what point you are going to get 1 will actually depend on R and C. That means the formula that we have, the working formula for finding out the time period will actually have R and C, okay, and it will also depend on the upper threshold and the lower threshold voltage, okay, as well as on the upper threshold and lower threshold voltage. So it will depend on these factors, and that's why we are going to have a formula which is actually a which involves all these factors, okay. So if we just look into the formula for time period, okay, this time period T is equal to 2 times RC, okay, the resistor and the capacitor that we have, into and natural log, okay, and then upper threshold voltage and lower threshold voltage is something which will actually define what is the value of beta. So 1 divided plus beta divided by 1 minus beta. So for your exam purpose, probably you just need to remember this formula. Okay? So this is important. We can actually derive it, but I'm not going to derive it. I'm just going to spare you from knowing the derivation of this. But then please remember this, okay, for numerical problems, okay. Please remember this. Okay. So this was actually a very short idea of Astable Multivibrator, but please remember, if you want to do a bit of self-study, please study Schmitt Trigger. Okay, DC Style is a good book. If you understand Schmitt Trigger, you will understand it even better why there is a charging and discharging when the value of voltage at this particular point is more or less, okay. But then it's not very difficult. For your exam purpose, this idea is actually very important, okay. So try to remember it in this sequence A, B, C, okay. Draw this figure, okay, draw it as clearly as possible as I've drawn, okay, and then I think that should be okay.